Suppose a 5 kilogram block is sent sliding up a plane inclined at theta equals 37 degrees, while a horizontal force F of magnitude 50 newtons acts on it. That's here in blue. The coefficient of kinetic friction between the block and the plane is 0.3. What are the A magnitude and B direction, up or down the plane, of the block's acceleration? The block's initial speed is 4 meters per second. C. How far up the plane does the block go? D. When it reaches its highest point, does the block remain at rest or slide back down the plane? So now we've got some free body diagrams. The first one includes or shows the unresolved vectors, and they're all in blue throughout the 3 free body diagrams given. The second one not only includes the unresolved vectors, but also then resolves them in green and gray. And that's here. And then the third one gets rid of the vectors that need to be resolved and just shows the green and gray vectors. Now, in order to find one of the things that the derivation below neglects is to demonstrate the equations for C and D. I kind of just show them in these free body diagrams a little bit and hint at them, but in the video I'll give a more detailed explanation. So for A and B, it's the classic gravitational resolving of the vector. We just call this theta, which has already been demonstrated in class, and then this is mg sine theta, mg cosine theta. But to resolve the pushing force, it requires a little bit more innovation. So we have that this is theta. So in order to get this angle, what we first do is we call this pushing vector and the bottom of the picture parallel lines, which makes sense because they are parallel lines. And then we say that this angle over here between the pushing force and the inclined plane is equal to the angle between the inclined plane and the bottom of the picture, and that's because the parallel lines yield congruent angles or something along those lines. I can't remember the explanation for it. And then the same thing is done between the pushing force and the inclined plane, this angle, and the angle between the pushing force and the C, and the resolved vector. And that's given by theta. You can see like here it's over here and then over there because of these parallel. And this is our transverse in that case. So that's how we get this angle to be theta, and then with that we just say that C is equal to FP cosine theta and D is equal to FP sine theta, based on our knowledge of trig functions. And sorry, I forgot to mention this, but this is an important thing that is kind of obvious about the problem, but still is worth mentioning, that the reference frame here will be, it'll be parallel to the inclined plane and perpendicular to it. The x-axis will be parallel here, with this side positive, this side negative, and the y-axis is the perpendicular one with this side positive, this one negative. There's my little negative sign. So yeah, that's the last we'll see of these two free body diagrams. From now on, we'll just refer to this one because it more concisely presents the information. So now we go to the derivation, and we're looking for the acceleration, the magnitude of the acceleration, and its direction. So we say that in the y direction, the net force is equal to the normal force minus b minus d, which follows our diagram. And we know that the net force is equal to 0 because the block is, well, it isn't like falling through the inclined plane, nor is it, being pushed off of it. So then we have 0 equals the normal force minus b minus d, and then we can just rearrange that in order to solve for the normal force, and then substitute in b and d. to get the normal force in terms of values we already know. And it's kind of hard to see down there, but we said that B is Fg cosine theta and D is Fp sine theta. So that's what Fn equals. Now in the x direction, the net force is equal to C minus A minus the frictional force. According to well, that's just because of the net force along the x-axis, I guess. And then you can plug in ma for the net force because of Newton's second law, and substitute values in for Ca and the frictional force, and then further substitute in values. Specifically for the frictional force, we can substitute in the previously found normal force for here, and that gives us the frictional force in terms of stuff we already know. So once we have that, we can plug in all of the values we've obtained up to this point, and then solve for A. And we get that A equals negative 2.06, which means it's accelerating in the, or downward, which is actually going to be the answer to B. And we also know that the magnitude is 2.06, the magnitude of acceleration, because we can, in one dimension, the magnitude of a force is just the absolute value of the force. So that's how we get A and B. I forgot to mention, and this is kind of just in case you were wondering how we know that the frictional force is acting in the negative direction, it's because in the problem it said that the block is being sent up the plane. And that's important because the frictional force could be acting in the opposite direction, which is something that we'll explore later in the problem. Now we move to part 2 for answer C. And this was asking, given a initial velocity of 4, how far up the ramp will the block go? This is just basic kinematics. We use v squared equals v naught squared plus 2a times the displacement. And we can do this because we know there's constant acceleration because none of our forces are changing. And we chose this equation because it doesn't involve time and we don't know time, so that's a plus. Now we can plug in 0 for the final velocity because we're looking for the point at which the block stops before turning around, or before moving backwards or just staying still. And we say that the block has an initial position of 0 because that makes our calculations easier. So now that we've done those 2 steps, we just have to solve for x, and we already have all the other information from previously in the equation. And we have, so we have v naught, and we also got a earlier on in the last part of the problem. And so then we can just solve for x, simplify it, and we get x equals 3.88. And now we move on to part 4, which is the hardest part, I'd say. And this is asking, does the block stay at rest, or does it go back down the plane? So this one I did a weird way, and it's kind of hard to see, but it works, and I'm sure there's a better way of doing it, but this is the one I went with. So we have, what we're going to do is we're going to assume a negative velocity, a velocity where the block is going down the ramp. And when we do that, we get the net force equals the frictional force plus C minus A, which is pretty much the same as what we had before, except now the frictional force is positive. So now we can plug in for C and A, and we're just going to leave the frictional force alone this time. So we substitute in, for C and A, and then we plug in for C and A, and we get the net force equals 10.44 plus the frictional force. Now, we know that the net force is going to be a positive number, because we know that the frictional force, the magnitude of the frictional force, is not going to be a negative number because it's a magnitude, and magnitudes can't be negative. So given that this is a positive number and this is a positive number, we know that the net force is a positive number. Now what that means is that the acceleration is also a positive number if the velocity is negative, if it's going down the incline. And we know that because the direction of the acceleration is the same as the direction of the net force. So now we can establish that the block stays at rest. And we can say that because we know that the block comes to, well, we already know that the block will come to a stop when it's pushed up initially because the acceleration is negative. But once the velocity changes directions, the frictional force also changes directions. So now the frictional force isn't necessarily acting downwards. It could still be acting downwards, or it could be acting upwards. And so the new frictional force makes it impossible for the block to accelerate downwards if the velocity is negative. That means if we push the block up, it'll go like this, where it slows down and then stops. And also, if we were to push the block down, it would also eventually come to a rest. By this I mean follow my mouse. So I'll demonstrate again since I didn't say that first. It'll either go up quickly and then slow down and stop, or it'll, if we push it, go down quickly and then slow down and stop. And this should show that the block will always come to a rest. It won't keep going forward and it won't go backwards. Regardless of what the velocity is, positive or negative, the block is eventually going to stop.